So, thank you for the introduction. I will talk a bit about the unified form language, and in particular some details of the automatic differentiation that is embedded in this form language, which adds automation of linearization to the FEniCS framework. So the long-term FEniCS vision is the automation of computational mathematical modeling, and the contributions from UFL to this goal is to improve on the automation of discretization and to add automation of linearization. So the main design goals of this project has been to improve the form compiler framework, in particular to make a form language that is independent of the approach we use to compile forms in FFC and the Cypher form compiler. It is to extend the language to be more expressive, so we can declare more nonlinear forms and PDEs that could not be expressed in the previous form languages. And we want to remove the form compilation bottleneck. Sometimes it can take a long time to compile forms, and at least we have improved it. I don't think we have quite removed it, but it's better. And in particular, we have added automatic differentiation of forms and expressions embedded in the language. So I will just give a very short, very brief overview of the language, but I won't go into details on all the operators. You can see the manual for those details. So to define any expression, you need to start with some basic entities, and we call those terminal expressions. So those are literal constants, like the scalars, or the identity matrix. We have some geometric quantities, like the facet normal and the spatial coordinate. And we have basis functions and coefficient functions. So if you know, I'm assuming some familiarity with the FEniCS from before, so if you don't know the difference between these, check the manual. Or the book chapter, which is in the printed book. So we have some operators. We have basic algebra operators. You don't need to use the mult function from FFC anymore. You can use these multiplication operators for basically anything. It does the right thing. You can have fractional powers, which you couldn't in tensor representation of FFC before. And we have nonlinear functions like exponential function. And we have some tensor algebra operators. And there are more of those. There are discontinuous Galerkin operators, jump terms, conditional operators. Are those implemented yet? No. So you can express it, but it won't work. We can look at that later. And there are differential operators. So one thing that some people don't quite like is that I've transposed the gradient compared to FFC. Also, we have differentiation of arbitrary user-defined expressions, which I'll come back to. When you have defined forms, you can transform it to other forms. So you can have, if you have a bilinear form, you can compute the action of this form on a function. So you get a linear form, and you can then assemble this linear form as a vector in Dolphin, instead of assembling the matrix and then forming the matrix vector product. And we have some other operators that, so text is wrong. You can extract the left-hand side and right-hand side bilinear and linear forms from a form where you just write everything as one expression. And you can compute the adjoint of bilinear form. This is simply done by swapping the test and trial functions. So differentiation of user-defined variables, of user-defined expressions with respect to user-defined variables is done like this. First you define some arbitrary expression, and then you declare a variable that takes on the value of this expression. So z and y, they will take on the same value when evaluated in the program, but they're not exactly the same. So if you define then an expression in terms of the variable set, you can differentiate it with respect to this variable, just like that. You can define variables with that are tensors as well, and then differentiation will mean differentiation with respect to each tensor component. And then we have automation of linearization, which is differentiation of entire forms. So that's a form transformation. I think you saw a very good example in the last slide from the talk before lunch. So I'll give a simpler example. If you have a discrete function f and functional m, then you compute and you want to minimize this functional, then you can compute the residual occasion or the gradient of this functional with just one line. And then you can compute the Jacobi matrix of this equation with just one line. So an example that is easy to follow and you can compute by hand or in your head is basically this functional here, f squared, which, if when differentiated, produces the load vector. When differentiated once more, you get the mass matrix. So the point here is that derivative of some form with respect to f means the derivative of the form with respect to each coefficient of the discrete function f. So with respect to the coefficients and not with respect to the function value. So one assumption that is made in the implementation here is that the domain and the integration is independent of the function you're differentiating with respect to. So what we're actually doing is differentiating the integrand expression. So this makes this the implementation for this differentiation is the same as for differentiation with respect to other kinds of variables. So another note about how this works. If you consider a finite element space with a basis, and you have a function, discrete function in this space with coefficient ui, and a basis function instance that represents some element in this basis, you can see that the derivative of this function with respect to one coefficient is one of the basis functions. And the basis function instance can represent one of those derivatives. So when you define a form that depends on a basis function, the form represents the form will be evaluated by the form compilers for each and every basis function in this basis. So we can do differentiation of a form that depends on a function once and replace the function with a basis function, and this will represent the derivative with respect to all coefficients.